Welcome students to Unit 3 of AP Chemistry, Intermolecular Forces and Properties. Today we're going to start by talking about intermolecular forces. Now in the previous unit we focused on intramolecular forces, the attractions that hold atoms together. We started by talking about metallic bonds. Now metallic bonds are not normally seen on the AP exam as an actual type of bond. It's simply how metals exist in nature. So our first intramolecular force that we talked about were ionic bonds. Now remember, ionic bonds are held together by electrostatic forces, where the strength of that force is proportional to the charges of the ions divided by their distance, their radii. Ionic bonds occur when there's a high difference in the electronegativity values of the elements involved. So normally these are between metals and non-metals, as a general rule of thumb. Now, all intramolecular forces happen to lower the energy of the atoms involved. There's a lower energy state when bonding. Covalent compounds form between non-metals, generally, and it's when there's a slight or no difference in their electronegativity values. Now, the strength of a covalent bond is determined by the number of bonded electrons. So a single bond would be the weakest and therefore the longest, a double bond would be shorter than that, and a triple bond is the strongest of our covalent bonds because they have the highest electron density between the nuclei. And again, atoms form these bonds to reach a lower energy state. Now this chart is in your packet on page 18, so if you weren't following along, pause the video and copy down these notes onto page 18 to fill out this chart. Now, intermolecular forces you've learned about before, specifically in biology. In biology, the attraction between molecules, their intermolecular forces, were commonly referred to as van der Waals forces. And van der Waals forces is a way to describe a vast amount of interactions between molecules. And it's kind of a dirty term in chemistry because van der Waals forces would be kind of like pointing at a forest and saying it's full of trees. Yes, obviously it's full of trees. What type of trees is important? And so in chemistry, while you can summarize all of these by saying they're van der Waals forces, please don't refer to intramolecular forces as van der Waals forces and then drop the mic. If you are asked about an intermolecular force, van der Waals is not enough to explain anything. You're going to have to go into detail about which specific tree is in the forest you're talking about. So the best place to start this discussion is to review van der Waals forces by watching the TED Ed video on how geckos are able to defy gravity, because it gives really good pictorial representations of the interactions we are going to be talking about here. So the first interaction to discuss is when a molecule is polar. Polar compounds are when electrons spend more time around one end of the molecule than the other. The side that has electrons around it more often is a little bit negative, so we give it a partial negative sign. The side that has electrons around it less are a little bit positive. Elements with a high electronegativity, like oxygen, fluorine, or nitrogen, are going to attract electrons more to them than elements with a lower electronegativity, like hydrogen here. And since hydrogen does not attract electrons to it so much, in water, Water has a partially positive end where there are less electrons found around the hydrogen, and a partially negative end where the electrons are found mostly around the oxygen. Since we have this asymmetrical distribution of electrons, you can't fold this way. Since this is asymmetrical, this forms a polar molecule. There is a dipole moment where electrons are more around the oxygen. So when a molecule is asymmetrical, it generally is polar. Lone pairs generally will often make things that would be nonpolar polar. So this is where you really need to remember your VSEPR models. Boron trifluoride is nonpolar because it's a triangle that lays flat, and while each fluorine has a dipole moment, the molecule as a whole does not, because the electrons are attracted equally in all directions, and so they don't actually move. So if a molecule is symmetrical, so for example if you have a tetrahedral, as long as all four terminal atoms are the same, you will have a nonpolar covalent bond. But if one of those terminal atoms is different, it's asymmetrical and becomes polar. A tetrahedral shape with a lone pair, so when you, for example, make a trigonal pyramid with ammonia, that lone pair actually attracts electrons more towards it. So lone pairs generally form a polar compound. When you have something polar with a partially negative end and a partially positive end, the positive ends can attract partially negative ends of other molecules. This is known as a dipole-dipole attraction, and is why things that are polar tend to have higher boiling point or melting point. Because in order for something to melt, you have to weaken the attraction between the molecules. And in order for something to boil, you have to break it completely. So melting point or boiling point can tell us a lot about a substance's intermolecular forces. Even in something nonpolar, we do observe attraction between the molecules because of what are known as London dispersion forces, which have to deal with the dispersion of electrons. In the TED Ed video, they discussed this by showing a nitrogen atom. Electrons are free to move about, and so at any given moment they might bunch up on one side of the atom or the other, causing one side to become a little bit negative and a little bit positive. This polarizability increases the more electrons you have. So this would explain why in the halogen family we actually see all three states of matter. Chlorine with only 34 electrons is less polarizable than bromine with 70 electrons. If I have 70 electrons, there's a greater chance that they will bunch up on one side of the atom, making that atom a little bit negative. Since it becomes a little bit negative, it forces atoms around it to become slightly polarized, and so the atoms around them will become more attracted. So bromine actually is a liquid at room temperature. Iodine is a solid at room temperature because it has 106 electrons. Those 106 electrons definitely bunch up way more than on one side of the atom or the other, making one side a little bit negative and one side a little bit positive, so the atoms around them respond by shifting their electrons as well, and they attract positive to negative, and thus iodine is a solid at room temperature. It has a higher melting point or boiling point. So London dispersion forces deal with the dispersion of electrons. The more electrons you have in an atom, the more electrons you have in a molecule, the higher the melting point or boiling point based off of London dispersion forces. So while every molecule experiences London dispersion forces, and London dispersion forces grow with the number of electrons, only polar molecules experience a true dipole-dipole moment. Now, polar molecules can influence or induce a dipole on something that's nonpolar. If I have something polar and I put it next to something nonpolar, that partially positive end is going to attract the electrons of the nonpolar molecule and induce a dipole and form an attraction. This is called a dipole-induced dipole, where something polar forces something nonpolar to become polarized. An example of this would be how oxygen is dissolved in water. Water is truly polar. It's got a pair of lone pairs on that oxygen, and the oxygen has a higher electronegativity than the hydrogens, so it has a truly positive end and a truly negative end. When a wave crashes against the shore, it traps oxygen molecules beneath the water. The water's hydrogen ends, that positive end, will attract the electrons in oxygen. And oxygen, therefore, will momentarily be polarized. This is how oxygen dissolves in water. But if you heat up water, those oxygen molecules move faster and faster. You weaken this attraction. That's why heating the oceans actually causes a decrease in the oxygenation of the water. If you have an ion and you place it next to a nonpolar molecule, ions have a true positive or negative charge, and of course that's going to attract electrons towards it, causing your nonpolar molecule to behave as though it were polar. This is known as an ion-induced dipole. Now, a special type of dipole-dipole interactions was seen in the video but not specifically talked about, and it's the attraction between oxygen and a neighboring hydrogen. Because oxygen is so electronegative and hydrogen is so not electronegative, when hydrogen and oxygen form a bond, almost all of the electrons, almost as though it was an ionic compound, leave the hydrogen. And hydrogen, a single proton, is left with a very, very, very small electron cloud around it. Since you have this almost naked hydrogen, almost naked proton, the electrons of a neighboring oxygen, nitrogen, or fluorine are very strongly attracted to it. The special type of dipole-dipole attraction we're discussing are what are known as hydrogen bonds. Hydrogen bonds are the strongest of the intramolecular forces you are responsible for knowing, and it's why water is able to absorb massive amounts of energy despite being a relatively small compound with very few electrons. Water, by any other standard, would have a very low boiling point or melting point, but because of this attraction for a hydrogen and a neighboring oxygen, this attraction is so strong that water is able to absorb massive amounts of energy. Hydrogen bonds happen between hydrogen and a neighboring nitrogen, oxygen, or fluorine. So I often don't call them hydrogen bonds because I feel like that's a misnomer. I call them Fon attractions because they happen between a fluorine, oxygen, or nitrogen, and they are such a strong attraction that they almost are a bond. That's why they're called a hydrogen bond, but they are not an actual bond. The hydrogen bond in this picture is the dotted lines. We show dotted lines in chemistry to note an attraction between molecules. So in this picture, we are showing the hydrogen bonds of water. So back on page 18, we can fill in some more notes. London dispersion forces, dipole-dipole interactions, and hydrogen bonds are the big ones to know here. And they relate most to boiling point or melting point. So you could think of relative strength in terms of things with a very high boiling point or melting point, and things with a very low boiling point or melting point. Now, London dispersion forces focuses on nonpolar compounds. If you are a nonpolar compound, the only attraction between your molecules is going to be London dispersion forces, which deals with the dispersion of electrons. There's an unequal distribution of electrons. This unequal distribution of electrons is known as polarizability. So rather than talk about how, they bunch up on one side or the other, you can say iodine has a higher polarizability than chlorine, and so iodine is a solid at room temperature because it forms an instantaneous dipole. Now, London dispersion forces, as well as dipole, induced dipole, or ion induced dipole, all increase with an increase in the number of electrons. The more electrons you have, the stronger your London dispersion forces. The more electrons you have, the more ions are going to shift those around. So a dipole-induced dipole is when a nonpolar compound, nonpolar molecule, is introduced to a polar molecule. And again, it has to deal with an unequal distribution of electrons, the polarizability. That's all going to hold true for these two. An ion-induced dipole is when you have a non-polar compound and an ion of some sort. Dipole-dipole attractions get stronger the bigger the dipole is. So increased strength with increased difference in electronegativity. And this will only happen between two polar molecules. Why does it happen? Because you have something that's something that's partially positive and something that's partially negative. Hydrogen bonds are a special type of dipole-dipole attraction that only occur between a hydrogen bound to an oxygen, nitrogen, or fluorine, and those oxygen, nitrogen, or fluorines are attracted to neighboring hydrogens bound to nitrogen, oxygens, or fluorines. This is really the same, that it is because of an attraction between something partially negative and partially positive, but it's a big partially negative and partially positive that drives this attraction. Now, the more places that you can have this occur, the stronger a hydrogen bond is. So it increases with the number of possible hydrogen bonds. So for example, ammonia has 3 hydrogens that can be attracted to the lone pair of a neighboring nitrogen in an ammonia, right? So like 1 versus, say, hydrofluoric acid, where you have 3 places that a hydrogen could be attracted to the fluorine. So increasing number of possible hydrogen bonds. Remember, the hydrogen bonds we're talking about are the attractions between the molecules. They are not an actual bond. Now, intermolecular forces ultimately drive what state of matter something is. Something with an extremely strong intermolecular force is likely to be a solid. This extremely strong attraction between the molecules holds them in place, and solids just vibrate in place. So they form a lattice-like structure. Now, since they are held in place, they take up a set amount of space, they have a definite volume, because they hold a specific shape. So solids, because of their strong attraction, have a definite shape and volume, and they form a lattice. Now, when you heat up a solid, those vibrations move faster and faster until the molecules are able to move around one another. This is an example of a liquid. Liquids have no definite shape because they're able to flow around one another, but they definitely take up a set amount of space. You can't compress a liquid because its molecules are as close together as they're going to get. That's the principle of hydraulics. Now, liquids have some interesting properties to them. A liquid will exhibit surface tension. The molecules on the surface of a liquid will be attracted to the molecules below by their intermolecular forces. The stronger the intermolecular force, the stronger this attraction. This is known as its surface tension. If you want to move this molecule, you have to overcome these attractions. And so liquids will exhibit a surface tension relative to their intermolecular forces. In middle school, you might have done the drops on a penny experiment, where you put a drop of water on a penny and you say, how many drops can you fit? Well, you can fit way more than you'd expect because water has hydrogen bonds. It's an extremely strong attraction. I think the record in my class when we used to do this was like 40 drops, but it really depends on the size of your drop. But you can definitely fit a lot of water droplets. Water has a very strong intermolecular force, but I always had the kids try again with oil. Oil has a much weaker intermolecular force. Oil is non-polar, so the only attraction between oil molecules is based off of their number of electrons, their London dispersion forces. So while water, you could probably get 40 drops, oil, you can get like maybe, if you're lucky, 4 drops on the penny, because water with a weaker intermolecular force experiences a lower surface tension. Liquids will also exhibit a viscosity, a resistance to mixing or flowing. An example of something very viscous would be honey. Honey has an extreme attraction for itself because honey is made up of sugar molecules which have a ton of electrons. Their London dispersion forces are massive. And so honey has a very strong attraction. It doesn't pour, it doesn't mix very well. But you're smart, you're pretty, gosh darn people like you. You know that if you wanted to make honey pour better, you could heat it up. Heating it up weakens those intermolecular forces, and therefore it flows, it becomes less viscous. Liquids will also experience capillary action. Capillary action is because of 2 principles, adhesion and cohesion. Liquids are cohesive. They attract to themselves. They have a strong intermolecular force, and that holds them together. So if you pull on one water molecule, you're gonna get a couple more. Adhesion is the fact that if you're a liquid, you probably have a strong intermolecular force. You probably attract other things, and so you attract to the sides of your container. You see this most when you look at a graduated cylinder. You'll see a meniscus. That meniscus is because the water molecules are attracted to the glass and therefore climb up it as they pull more water molecules with them. That is adhesion and cohesion at work. This is known as capillary action. It's also how roots work, by the way. Now, liquids have these properties because of their intermolecular forces. If you break all the intermolecular forces, if you heat up a liquid to the point that all its intermolecular forces collapse and fall apart, you will form a gas. Gases have no intermolecular forces, and so they spread out as wide as possible. This is why you can put your head on your pillow. Your pillow is made up of mostly gas. Your pillow compresses, but when you release that pressure, the gases fill it back up. Gases can expand and contrast because they have no intermolecular forces. So on page 18, I also am asking you to do a particle sketch of what does a solid look like. Remember, in a particle sketch, we're going to show molecules as circles. Circles that overlap are a single molecule or compound or element. Circles that are near each other shows how packed together they are based on their intermolecular forces. So a solid, you would show all packed as tight together as possible. And remember, solids have a very strong attraction, so they will have a definite shape and take up a set amount of space. Now, using those exact same 10 circles, what would a liquid look like? With 10 circles, what would a gas look like? You can go ahead and pause the video and fill in your particle sketches. Now, a vast majority of this unit is going to be on gases. Gases have some very unique properties, and we will use them to predict how a gas will fill or not fill its container. We explain how a gas behaves by the kinetic molecular theory. Remember, theories are an attempt to explain why things behave the way they do. The kinetic molecular theory says that a gas is ideal if it follows 6 concepts. Gases, so the first concept of a gas is that gases are made up of lots of molecules, but they have very few electrons. Since they have very few electrons, they experience almost no intermolecular forces. They have no intermolecular force if they are truly ideal. Since they have no intermolecular forces, they take up an infinite amount of space relative to the size of the actual molecule. Gases are mostly empty space. And they are constantly in motion within that space. They'll move in a straight line till they collide with one another or the walls of their container. When they collide with each other or the walls of their container, they will exhibit what are known as elastic collisions, where they bounce off with the same amount of energy with which they collided. This energy is conserved when they collide with something, because if it wasn't, energy would constantly decrease as collisions occurred. And if you took the average of all the kinetic energy, all of those collisions of a gas, you would come up with something relative to its temperature in Kelvin. So Kelvin, remember, is take degrees C plus 273. It's also on your formula sheet on the right hand side, about a quarter of the way down. You'll see K equals degrees C plus 273. Now, any gas that obeys all 6 of these ideas is said to be an ideal gas, right? But there's really no such thing as an ideal gas. In all honesty, no gas behaves ideally. Every single gas deviates, because the kinetic molecular theory says that gases have no intermolecular forces. However, that's not true. They have a negligible intermolecular force, meaning it's almost nothing, but it is still something. Gases are still slightly attracted to one another, so they will pull on one another. And so if you ever are asked, hey, our gas's volume was less than calculated, that's most likely due to the fact that that gas has some intermolecular force. Another problem with the kinetic molecular theory, where gases will deviate, is sometimes our volume of gas will be more than we anticipated, especially if we're dealing with a very large gas. That's because we say a gas molecule takes up a negligible amount of space relative to the volume it's in. But some gas molecules are fairly large, and they do take up some space. So no gas behaves ideally, but you can force a gas to behave ideally by holding it at a high temperature. At a high temperature, those intermolecular forces will be negligible because the gas will be in so much motion that it will be moving so quickly that it can't be attracted to one another. And at very low pressures, if there's nothing pushing on the gas, a gas will expand to fill up a lot of space, in which case they are not going to come in contact with one another, and that intermolecular force will drop. Also, they'll fill up a large amount of space, so the actual volume of the gas is probably negligible at that point, or almost zero. So page 18 has you finishing this by drawing a picture for the postulate. So if you want to say they have no intermolecular forces, you could show gas molecules separated by one another, being like, I don't love you. Drawing your picture is up to you, completely subjective. Now, gases will fill the space they're in. They will do this by Brownian motion, colliding with one another. So this process is known as diffusion. If you have a gas with high concentration, it will eventually spread throughout the room. You can see this when I brew a pot of coffee in your class. My coffee cup directly above it has a lot of aromatic compounds that smell like coffee. However, over the course of the period, that high concentration above my cup, when they bounce into oxygen and carbon dioxide molecules, will begin spreading throughout the room. By the end of the period, everyone in the room can smell the coffee over my cup. Another way that gases will spread is through effusion. Effusion is movement through a small opening. You can often see this if you had a birthday party at your house. For your birthday party, your parents might have put balloons around your mailbox, and during the party, those balloons are full of helium and they float. But there's not just helium in there, there's also a little bit of nitrogen, a little bit of oxygen, a little bit of carbon dioxide. But by the next morning, your balloons are shriveled up. They're not empty, they still are round, they still look like balloons, but they're no longer floating. Now, the reason for that is because the helium was able to make it out. On the surface of your balloon, there are small pores. Those small pores, the helium, being one of the smallest atoms in your balloon, are able to go through that small opening way faster than the nitrogen or oxygen or the carbon dioxide, because carbon dioxide is a massive molecule. It won't fit through a small opening nearly as fast as helium. This rate of effusion, being inversely proportional to molar mass, is known as Graham's law. Graham's law simply states that the rate of effusion is inversely proportional to molar mass. So large molecules like nitrogen, oxygen, carbon dioxide will effuse slower than helium. Now, changing these intermolecular forces ultimately results in a phase change. So the amount of energy it takes to go through a phase change is known as the heat of that phase change, or the enthalpy of that phase change. If I want to melt something, melting is known as fusion. So the heat of fusion is the amount of energy it takes to weaken the intermolecular forces of a solid enough that they're able to flow around one another. Opposite this heat of fusion is the heat of solidification, the amount of energy it takes to freeze something, how much energy do I have to remove to strengthen those intermolecular forces to hold the molecules in place. If you have a liquid and you heat it up to the point that you overcome all the intermolecular forces, the amount of energy it takes to do that is known as the enthalpy of vaporization, because I'm boiling this substance. Now, running perfectly opposite of that, meaning if it took 1,000 kilojoules to vaporize something, I would have to remove 1,000 kilojoules to turn it back into a liquid. This is known as the enthalpy of condensation. When you remove something, it's given a negative value. It's coming out. And when you heat something up, you add energy. It's a positive value. If you add energy, that's known as an endothermic process. So when I want to boil water or when I want to melt ice, I have to put energy into that. That's an endothermic reaction. If I want to condense gases back into a liquid, or I want to freeze my liquid, that is going to take energy. So that is given a negative value. Energy is coming out. So we call that an exothermic reaction. Energy is going to be pulled out. Now, some intermolecular forces can be overcome very quickly, and that's when a solid can go directly to being a gas. For example, iodine. Iodine crystals are a purplish crystal that, even at about 70 degrees, will begin to smoke. They'll begin to undergo the process of sublimation. Sublimation is when a solid's intermolecular forces break almost instantly and form a gas. You can see this easiest with dry ice. Dry ice you buy at the grocery store, Harris Teeter. It's condensed carbon dioxide that is held together by only pressure and London dispersion forces. If you remove that pressure and then leave it on the counter, it will instantly turn back into a gas. Dry ice sublimes. Deposition is the opposite of this. The enthalpy of deposition is the amount of energy it takes to take a gas and hold those molecules in place to turn them into a solid. You can see this in the winter when there's frost on your car. The water vapor in the air hits the surface of your car and loses enough energy so quickly that it skips its liquid phase and goes straight to being a solid. So with that, we are now done with Unit 3.1. Please finish page 18, and I'll see you next time when we talk about gas laws and using that kinetic molecular theory.